Alrighty, gang, another ideal gas problem in physical chemistry. We're going to jump right into it. We have a gas mixture of helium and argon weighing 5.00 grams, so that's collectively, occupies a volume of 10.0 liters at 25 degrees Celsius and 1 atm. And with this information, we want to know the mole fraction and the partial pressure of helium, the helium gas. Now, it doesn't say that we need to treat them as ideal gases, but in a question, if it doesn't say that, just assume that they are if it doesn't tell us otherwise. So we're going to start off with PV equals nRT, and with this here we're given a temperature, we're given a pressure, and we're given a volume, so we can calculate how many moles there are in this. So we can't get the mole fraction or partial pressure yet, but just straight up with the ideal gas equation we can calculate the moles. So that's what we're going to do. We're going to calculate the total moles, and then we're going to use this mass here to find out what the mole fraction is. But let's find out what the moles are first. So moles is PV over RT, and the pressure is 1.00 atm. The volume is 10.0 liters. And R, now we need to use the right R here. We're in pressures of atm, and volumes of the volume is in liters, and then temperature is always in Kelvin. So if we convert this to Kelvin, we add 273.15 Kelvin to it, so it's 298.15 Kelvin. So we need our R, the units of our gas constant, R, to match the other units here. And it should be given to you, otherwise you have to convert. But here we have 0.8206, and the units are liters atm per mole Kelvin. Sorry if that's squished in. This says liters atm over moles Kelvin, so the liters cancel out, the atm cancels out, the Kelvin cancels out, and we're left with 1 over moles, which becomes moles because this is in the denominator. Right. So we will plug that in, and we have 1, don't have to really include that, 1 times 10 divided by 0.08206. I put parentheses in the denominator here, times 298.15, close brackets, equals 0.4087, 0.4087, 3 sig figs, and this is how many moles we have here. So this is total moles, right? So this is like our NT, total moles. Now, we need to know how many moles there are of helium. So how can we do that? Well, we know that this is the total moles. So we can say moles of helium plus moles of argon has to equal 0.4087 moles. That's the total moles. Add up the moles of each gas. This is how many moles there are. But this is one equation, and we have 2 unknowns. So we need another variable here. And we're going to use this mass here in order to get another equation that has moles in it. So the mass, the total mass adds up to 5 grams, which means mass of our helium plus mass of our argon, that total mass has to equal 5.00 grams. So far, so good. So now, how can we relate mass to moles? Well, we can use our good old friend, the molar mass. Molar mass equals mass over moles. So if we solve for mass, the mass of a compound is equal to its molar mass times the number of moles there are. So we can say that rather than writing mass of helium, we can say this is equal to the moles of helium times the molar mass of helium plus the moles of argon times the molar mass of argon. My pen just cut out on me. There we go. Molar mass of argon equals 5.00 grams. All right, so now we have 2 equations with 2 unknowns. So in theory, this is solvable. And we're going to plug this in here. So we're going to keep moles of helium right here. And the molar mass of helium is 4.0026 grams per mole if you look on the periodic table. Now, we're going to substitute what the moles of argon is. So if we solve for the moles of argon, it's going to equal the total moles minus the moles of helium. So it's 0.4087 moles, total moles minus the moles of helium. That's how many moles of argon there are. And then we're going to multiply it by the molar mass of argon, which is 39.948 grams per mole. And all of that has to equal 5.00 grams. Great, so now we have one equation with one unknown. So we can collect like terms here. I'm going to do this a little bit quick, but see if you can see what I'm doing here. You can do another couple steps if you like. But this is a term with moles of helium. And then if we distribute this in, this will become a term with moles of helium. So we're going to factor these two numbers out because this is a term and this becomes a term and this becomes a term here. So we could just write it as 4.0026 grams per mole minus 39.948 grams per mole. And it's tempting not to include units, but I strongly recommend including the units all the time, because sometimes that gets us by unit analysis, right? Plus, now I'm going to multiply this 39 by this one because we're distributing this in. So 39.948 times 0.40. It's sometimes best just to do one calculation at the very end. There's less chance of losing digits, losing precision, that sort of thing. I'm just going to run this in and keep a couple extras. So 16.32, let's call this 327. So 16.327, and that'll be in grams because this is grams over moles. And all of that equals 5.00 grams. So moles of helium, you're going to 5 minus this 16 here. 16 minus 5. But this will be negative because moving this 16 over to the other side makes it negative. So it would be negative 11.33. 11.33 grams divided by whatever this is here. 4.0026 minus 39.948. So that's negative 35.945. 30, did I say 35? 35.945. And this is in grams over moles. And look at that, our units work out. Grams cancel, and then moles go on top. So we have 11. The negatives cancel. So the negative and the negative just makes it positive, which is a good thing. We don't want negative moles. Divided by 945. 0.3152. 3152. We'll keep 3 sig figs. This is a 2 moles of helium. Now that we know how many moles of helium there are, we can proudly obtain and easily obtain the mole fraction. So the mole fraction of helium, it's equal to, there's 2 ways for an ideal gas, the moles of helium divided by the total moles. The other way is with pressures, which we'll use shortly. So we know the moles of helium, 0.3152. Oh, this should not be over the 1. It should be over the 5. 3 sig figs. Moles over the total number of moles, which is 0.4087 moles, which is, let's see here, 0.3. Oh, I already had it in my calculator. Divided by 0.4087. 0.87 is 0.771. 0.771. Only 3 sig figs, but we'll keep that 2. We don't really need to keep it. But anyway, your answer is 0.771. So that's part A, that's the mole fraction. And the partial pressure, for an ideal gas, the mole fraction is also equal to the partial pressure over the total pressure. We could write Xe is also equal to the partial pressure of helium over the total pressure. Well, we know what the total pressure is. It's just 1.00 atm. So if we plug this in, the mole fraction is 0.771, and the partial pressure is what we want. The total pressure is 1.00 atm. So it's literally just this times 1. So the partial pressure of helium is 0.771 atm. All right. Hope you enjoyed it. Cheers. See you in the next video.